doped silicon p-n junction has Na, that is 5 into 10 power 17 per centimeter cube, and Nd, that is donor doping, that is 10 power 17 per centimeter cube. The junction has a cross-sectional area of 10 power minus 4 per centimeter cube. Sorry, cross-sectional area of 10 power minus 4 centimeter square, and has an applied reverse bias of 5 volts. The total junction capacitance is, here the total junction capacitance is nothing but epsilon A by depletion width, that is W. Here epsilon is nothing but epsilon naught into epsilon R. Here epsilon R is 11.7 for silicon. Here W is 2 epsilon VBI plus VR divided by Q 1 by Na plus 1 by Nd. This. Here VBI is nothing but Vt natural logarithm of Na Nd by Ni square. So if we calculate this one, we will get it as 0.856. Again, if we substitute this built-in potential into the equation of the depletion width, that is W, we will get that as 3.01 into 10 power minus 5 centimeters. So we got an area of 10 power minus 4 centimeters square. So after substituting all these values, we will get a junction capacitance as 3.5 picofarads, that is option D is correct.
Find the value of lambda for which the given equations are consistent. So the given equations are x plus y plus z is equals to 6, x plus 2y plus 3z is equals to 10, and x plus 2y plus lambda z is equals to 12. Now, in order to find the value of lambda, what we do is we'll make the coefficient matrix, determinant of the coefficient matrix to 0. If the determinant of the coefficient matrix is 0, then the equations will be consistent. So the coefficients are 1, 1, 1, then 1, 2, 3, 1, 2, lambda is equals to 0. Let us apply row operations. We'll apply R1 tends to R1 minus R2 and R2 tends to R2 minus R3, so that the simplification will become easy. So if I apply R1 minus R2, it will be 0, minus 1, minus 2. Similarly, R2, 0, 0, 3 minus lambda, 1, 2, lambda is equals to 0. Now, instead of expanding horizontally, what we do is we'll expand vertically, so that the simplification will be easy. That means we need to expand only 1. So if I expand along 1, it will be minus times of minus 1 into 3 minus lambda minus minus 2 into 0, that is equals to 0, which implies 3 minus lambda is equals to 0, which implies lambda is equals to 3, which is option E.
For the block diagram shown below, the limiting value of K for the stability of the inner loop is found to be in between X and Y. The overall system is stable if and only if. See, for the inner loop characteristic equation is S minus A, S plus 3A, S plus 4A plus K is equals to 0. For the outer loop characteristic equation is similar, except K is replaced by 2K because it is going to be added twice, because of the feedback is going to be repeated twice. So if K is in between X and Y, 2K is between X and Y for the outer complete system to be stable. So K should be X by 2 greater than less than Y by 2. Hence option B is correct. What path transfer function of a unity feedback system is? Here the given transfer function is nothing but an open loop transfer function whose pole locations are at S equals to 0 and plus or minus 1. Similarly, zeros are located completely in the left half of the S-plane, that is S equals to minus 5, minus 3. Whereas out of 3 poles, 1 pole is located on the right half of the S-plane. So if we plot, this is 1, this is minus 1, this is 0. here minus 3 minus 4. So the odd portion, the portion of the root locus is going to lie if the number of poles to the right side of number of poles and zeros to the right side of it is odd number. So this is going to be in the root locus, as well as this is going to be in the root locus, as well as this is going to be in the root locus. So this moves in this direction. There is one breakaway point as well as one break-in point. So the root locus is going to be in exactly symmetric about the real axis of the S-plane. So this is the root locus corresponding to this forward path transfer function. The 4:1 mux below implements the Boolean function which is shown below. The inputs to I1 and I3 is here. If you want to solve, see, out of the 4 variables, 2 variables are connected to the control lines. So what we will do is, by using K-map, we can easily handle this one. See, let's see WX YZ. So this is 0 0 0 1 1 1 1 0. So this corresponds to I0 line, this corresponds to I1 line, this corresponds to I3 line, this corresponds to I2 line. So after substituting or entering the given min terms, that is 4, 5, 7, 8, 10, 12, 15, here from this I0 equals to 0, so it is already given in the question itself. So we have to find out the I1. So I1 is nothing but this is 0 0 0 1 1 1 1 0. So look at this row, this particular row. Exactly, I1 is, if you combine these two things and these two things, you will get it as, it is nothing but y bar plus z. So I3 comes to I3 here is y exclusive NOR of z, and the I2 is nothing but z bar. Hence y bar plus z comma y exclusive z. Hence, see here it should not be there. So option C is correct. Is a parallel combination of an inductor and the capacitance whose values are 4 henries and 1 farad respectively. At what frequencies is this impedance becomes infinite? So in order to explain this, first of all we have to consider a parallel combination of LC network. Okay, in Laplace domain we can represent this as SL, this can be represented as SC. Here we know L as well as C values, so here Z of S is going to be parallel combination of both SL 1 into 1 by SC, SL plus 1 over SC. So SL S square LC plus 1. So the impedance becomes infinite whenever S square LC plus 1 is equals to 0. That means S equals to S square is equals to minus 1 by LC, that is plus or minus j under root 1 by LC, which is j under root 0.25, which is plus or minus j.5 radians per second. Hence both option A and B are correct. Hence option D is correct. That is option D is the correct answer.